So when you're buying a custom-made kitchen from a well-known Swedish furniture company, there's this nice website you can use to sketch your space and place cabinets and other furniture, make some styling choices, and finally get an appropriate price suggestion for that. So that's pretty convenient, isn't it? Now, if I want to buy something else, let's say a spiral staircase or an industrial robot, or maybe an underground mining machine, then they must be the same thing as with the kitchen, mustn't it? Let's have a look. Oh, okay. So there's no nifty website I can use to do that. But how hard can it really be to just specify what I need? How hard can it possibly be? I mean, I just have to, let's see here, I have to decide on the diameter of that spinner thing and the width of the impercolator, the pressure used in the hydraulic puffers, and the length of the reticulated splines. And that must also be very carefully matched with the circumference of that gadget, because otherwise it could just make or break the whole deal. So how hard can it be? Oh, okay. It's a bit tricky, I admit. So I'm just going to ask a few engineers and have them work on this for me and sort this out. And they'll get back in a few months or so and give me a product specification and a price suggestion, a quote. Oh, it's here. Wow, that's a neat little thing. Wow. Okay, so let's see here. Wow, I think the performance could be really great for my application, actually, and it seems like it can provide some fairly nice value. But you know what? I don't want it. So we have a small problem here. I, the customer, must wait for the engineers to make their work, and the hard work put in by the engineers to make that quote has a large risk of going down the drain if I'm not interested in accepting their offer. So what if we could have something like this kitchen website, but adapted for something very complex, like the mining machine, where I just supply the tool with everything I know about my very own problem. I have a computer make the hard decisions for me and then suggest the very best possible solutions, and ultimately leaving me to call the final shots. And that is what my thesis is about, if I'm allowed to simplify a bit. But let me explain further then. So my name is Ole Widner, and this is the seminar on my Licentiate thesis titled on multidisciplinary optimization in engineer-to-order product configuration. And there's a few tricky words, so let's deconstruct it together. I will start by taking a closer look at the engineer-to-order product family and product configuration, and then we'll go to the multidisciplinary optimization and how it all can be combined. But before we can talk about product configuration, let's talk about product customization. And what's that? Well, let me tell you what it's not. So the most common way of producing and buying products is by selecting from a set of pre-designed and manufactured products. And these are made to stock. You can just go grab them on the shelf. And they're designed, manufactured, assembled, and put on stock before you even get to have an opinion about them. And your degree of freedom as a customer lies in selecting the one you like. Now, for some products, this approach does not provide enough freedom and not provide enough value as a consequence of that. So instead, you need to customize, which means to build, fit, or alter according to individual specifications. So to go to an extreme, when you're investing in an oil tanker or maybe a water treatment plant, you usually can't buy them off the shelf, but you rather have them customized. And they're even fully engineered to your own needs, which means that a considerable amount of brain power is going into the design of the product. And thus they are engineered to order, or ETO products. But what about that Swedish kitchen then? Well, it's also a customized product, and because all rooms and tastes are not made the same. But as a product, what makes it different from the oil tanker and the water treatment plant? Well, it's a lot of things, obviously, but what I would like to focus on is that it is actually engineered and manufactured in configurable components before the customer can express their wants and needs. And here the customer does that by combining different components with each other into a complete product. And the way these components are combined is through the help of a specialized computer system called a configurator. Seen on a more abstract level, the purpose of the configurator and the configuration process is to combine predefined entities and define their variable properties while obeying constraints and legal interface combinations in a way that satisfies given requirements. Or put in another way, to transform an abstract product description using relatively few attributes to a concrete product specification using relatively many attributes. And configurators are examples of design automation systems, which can refer to a wide range of reusable IT systems developed to support the design process. And another category of design automation solutions employs optimization. So that is usually termed design optimization. And design optimization is a method for finding design solutions that are best or optimal according to some numeric measurements, which are usually referred to as objective functions, or F in this case. And we usually say that these depend on design variables X. And the values of X are varied by an optimization algorithm to find these very best F values in a smart way. Additionally, some other fixed parameters P may also impact the value of F. And to make things harder, one often has to accommodate that X may only take values within a certain allowed design space, and that some constraint functions G and H must be unequal or equal to certain values. In multidisciplinary design optimization, or MDO, a set of computational models are connected with each other and used to get these values of F, G, and H. And quite often the set of models and their connections are visualized using the kind of diagram you see here on your right. And the symbol Y here simply refers to any other model outputs that are not used by the optimizer. And we will get back to that. Going back to configuration for a while, the literature makes clear that configurators are commonly used for the type of customization where the product consists of multiple predefined and assembled components or discrete solution spaces. And some even claim that this is the only way, the only rational path to take for customization. And this type of configuration is commonly solved by using rule-based approaches. However, ETO products are characterized by continuous solution spaces. And some authors point to the shortcomings of rule-based approaches here. So instead, optimization-based configuration has been proposed as a path forward. And that brings us right into my research questions. So first, what is the state of art of optimization-based configurators? What do we have? And number two, what functionalities are needed within optimization-based configurators? What do we need to be able to do using these tools? And three, how should an optimization-based configurator be designed and implemented? So how have I approached these questions then? Well, being a researcher, I turned to science. Well, as I alluded to in my preface, I just want to make clear here that my research is not within the natural sciences, but rather within the sciences of the artificial, as termed by Herbert Simon. And I'm not trying to understand and explain some metaphysical mechanics of the world, but I want to understand how we can make new things and change the world, or put more realistically, a very small part of the world. And that small part of the world that I want to change concerns why and how we can use optimization to solve configuration problems in ETO businesses. That is, I want to understand and change the way we design something. And a common way of structuring research that aims to understand and change design is by utilizing the design research methodology, or DRM, formulated by Lucian Blessing and Amaresh Chakrabarty. So the DRM suggests that design research should be conducted in 4 iterative stages. So first, The research is clarified by defining the research scope, goals, and criteria against which to evaluate the research outcomes. And then the first descriptive study aims at describing a pre-existing situation and then identifying the key factors to influence through a design support. That is a tool or a method. And the prescriptive study aims at prescribing a design support solution that addresses the key factor identified in the first descriptive study. And last, the second descriptive study then aims at describing the new situation after introducing the design support and identifying necessary improvements. So you clarify, you explain how it is now, you introduce some change, and then you evaluate what happened due to that change. So what kind of situations am I trying to understand and develop support for them? Industrial situations. So why not use the industry as a laboratory? As it turns out, there is a special case study method named exactly this way for this particular scenario. Because case studies are frequently used when it is desired to study a particular phenomena within its context, or when it is desired, it's not feasible to separate it from its context. And since I am interested in industrial design processes, it is neither desired nor feasible to fully separate what is happening from the context where it is happening. So the industry as a laboratory, formulated by Colin Potts in 1993, captures this by viewing the industrial part in a twofold sense, as a source of inspiration and as an application testbed. And in this way, the researcher can continuously get insights into challenging problems, apply new engineering methods, and evaluate the results in a realistic setting against general hypotheses. So without further ado, let's get into the results of applying this approach, starting with my first paper. And paper one is concerned with the configuration of spiral staircases, and more specifically, how to support the configuration process with optimization and value-driven design. Now, spiral staircases might look fairly trivial, so why are they interesting to consider? Well, first of all, each delivered staircase is made to fit a unique building, and that means you can't simply solve the problem once and then put them on stock. And second, they consist of both prefabricated and customized parts that can be combined in an almost infinite number of ways. All these parts must be configured in a way that makes the floors start and end at the right places. And the staircase must conform to regulatory and usability requirements. While these requirements are well defined, you must consider all of the floors and all of the requirements at the same time, since they are interacting with each other. And the process of doing this manually is repetitive and time-consuming, so it's easy to make mistakes, and mistakes increase lead time. The way we approached this problem was to formulate a configurator concept where the user supplies only their problem and gets back evaluated solution concepts. So what happens inside that configurator box then? Well, using a well-defined representation of the customer's requirements, a pre-processing routine builds an optimization problem, which I'll get back to in a short moment. And that problem is then solved, generating thousands of design proposals. To simplify the human decision-making, the set of designs is post-processed, leaving only the feasible and Pareto optimal designs for the engineer to choose from. So let's take a short intermission and very briefly look at the multidisciplinary optimization formulation built as part of this configuration process. And to optimize your listening experience and satisfy the time constraints, I refer you to the paper for the full details here. But it consists of an NSGA2-based multi-objective optimization solver, which feeds the design variables to 4 models. A geometry model infers dependent geometry parameters that together with the design variables give both the cost and the usability of a specific design as outputs. And these are then used as input to a value-driven design model that provides a value estimation for each design proposal, which brings us back to the configurator perspective. Because after building the optimization problem, solving it and gathering the data, and then post-processing that data, we have a curated set of designs left to choose from. And a key point here is that these routines are carried out automatically without additional user input. So that means the engineer can input the requirements, go for a walk or a coffee, and come back with a set of good designs on their table. But don't worry, that engineer will not be replaced by the computer, because there is still ample room for human decision-making, and by including a value estimation, the stakeholders can be informed of the relation between technical traits and product value, and base their decision-making on both factors. And I will get back to this configuration framework adapted for another application in a while, but first let me talk about the results of using this approach. So we used requirements data based on a real-life configuration scenario, a staircase between 3 floors, and we had access to an existing baseline design prepared by an experienced engineer in the field to compare against. And what we're seeing here is a scatter plot of all feasible designs, which means that every dot here represents one single design candidate that could actually work. On the x-axis, we have the reservation price, and on the y-axis, we have the manufacturing cost, and both relative to that baseline design. And the designs marked A to E correspond to the design with the highest surplus value for every occurring radius. So they're all different, but also optimal in some sense. But my main point is, however, that the approach demonstrates the capability to identify designs that resemble and even dominate a human-made baseline design in a fraction of the time needed for the human engineer, while still offering a human to make the final design decisions. So we now have a starting point for discussing and defining the procedure using multidisciplinary optimization in configuration. So let's move on to the second main application, the mobile miner. And this family of machines is the subject of papers 2 to 3, or 2 and 3, and they are specialized machinery for mechanical rock excavation used in tunneling and mining. And I explained right in the beginning that these machines are complex to customize, since there are many aspects to consider, and even more than for the spiral staircase. And the machine must work for the customer's unique rock conditions and satisfy a large number of constraints, and in the end, provide value. So to provide some perspective, the engineering time needed to provide a specification is measured in man-years, multiple man-years. And a particularly challenging aspect lies in the dimensioning of the cutter wheel in the front of the machine, and pictured here, since the number and the placement of cutters heavily impact the machine's performance. So the configuration framework outlined in paper 1 was revisited, and a user interface was added to facilitate the input of an abstract product description, as well as the output of concrete design specifications. But we have an abstract optimization problem right in the middle of the figure there, so let's make that a bit more concrete. And there's a lot to digest here, so let me briefly walk you through this computational model that is part of my work. So based on the user inputs, the cutter wheel is designed to accommodate the wanted tunnel dimensions. And then the excavation process is simulated and the cutter lifetime is estimated, which in turn makes it possible to provide basis for calculating the total cost of ownership and assemble all design solutions into a format that can be post-processed and returned to the user. And the computational accuracy of this formulation has been verified in cooperation with domain experts and deemed to provide good enough accuracy for this kind of application. There are 2 points that I want to make, though. One key aspect is that the data used for the decision-making made by the optimizer is not exactly the same as that made available for the human decision maker. So we still need a human to make the final decisions, but we use a computer to provide good solutions to choose from. And the other key point here is that the number of models and variables is quite large. So the number of known and unknown variables amounts to around 200. So it emerged the need to develop some kind of framework for managing the metadata used in both pre and post processing of the optimization problem and its data output. So instead of repeating the variable metadata every time it occurs throughout the optimization formulation, it is instead stored in a central registry and referenced where needed. So an added benefit of this is that the metadata can also be used to facilitate the post-processing of optimization data. And speaking about post-processing, so what's the purpose of that now again? It is to present design specifications to a user, of course. Now let's take a look at a configurator prototype implemented for the mobile miner. And using this graphical user interface, the user can input their specific application parameters and design variable bounds and just start optimization. And a few moments later, the user can get an overview of the generated solutions. They can then filter for the Pareto optimal solutions and take a closer look at some of them. And to compare the selected designs, the user can employ the interactive 3D view or the interactive performance plots. And some basic design data are available, as well as the basis needed to calculate the total cost of ownership. And for further analysis, the design data can be exported to every engineer's favorite tool, Excel. All right, so isn't this enough then? I mean, of course, things can get better, but how? So we tried to answer that question by conducting a focus group workshop and individual interviews with mobile miner engineers to identify the needed improvements from this prototype. And by analyzing and generalizing the responses, we could identify the 5 most important needs. So first, the tool is internally consistent and functions reliably, which we can translate to it works. I mean, that's kind of obvious, but it needs to be there. And number 2, the tool expresses inputs and outputs in consistent and relatable formats. So from an engineering perspective, it means that I can make sense of the output and use that to do my work. And 3, the tool supports the user in changing the model composition used to evaluate inputs and outputs, which we can simplify to, I want to know something else than this formulation tells me. So we need that possibility to know something else. 4, the tool supports the quantification of uncertainties and their effects on product performance. So we need to happen, what happens if something else happens? And 5, the tool presents the factors limiting the product performance. Why isn't this design better? And what should I change to make it better? And so much about the needs to consider for an optimization-based configuration system in itself for now. But what about the process of developing those? So let's move on to paper 4, which is on the development and deployment of design automation systems, such as optimization-based configurators. The paper 4 summarizes 5 industrial academic case studies, whereof the spiral staircase and mobile miner applications are 2. And 2 other cases concern additive manufacturing of structural airplane brackets and hydraulic pumps, respectively. And finally, the last case concerns host routing in vehicles. And some common issues and challenges raised during these projects are highlighted and mapped along 2 dimensions. So first is the life cycle stage dimension that ranges from issues in the initial development activities of identifying a problem and devising a solution to the deployment of a system in the industrial environment. And second, the domain dimension ranging from organizational issues associated with project and knowledge management to technical issues regarding connection and definition of software components. And by considering these dimensions as orthogonal axes, we can get 4 fields onto which we map some common issues. So starting in the lower left corner with the organizational aspect of development, the most notable issues relate to the difficulty of managing the development of a new solution to a new problem. And in the study cases, establishing clear goals has proved to be challenging. and probably due to a lack of knowledge in the early phases of development. Likewise, settling on a clear definition of a minimum viable design automation product seems to be a hard task. And both of these difficulties seems to indicate that the design paradox is fully at play when developing design automation systems. So staying in development, but moving into the technical domain, uncertainties still play an important role. And often tools and software that are new to the researcher are to be integrated. And this in combination with novel methods can create issues with getting stable development environments in place. And after overcoming this hurdle, a very important factor remains, which is that of handling model integration in a flexible way, and to enable rapid iterations in the development process of the design automation system. Also playing into this is the issue of computational complexity, contributing to longer lead times. Then, transferring the design automation system to an industrial partner requires it to be packaged from its development environment into a usable, independent system to be used on the partner's premises. And this has been identified as an issue in all of the studied cases, especially due to unexpected incompatibility issues between subsystems. And ensuring that the design automation system remains highly maintainable and flexible is therefore seen as crucial for a successful implementation, since both early and late changes to the system must be accommodated. Finally, getting the design automation system to actually support the product development process in the long term turns out to be hard, especially so when the target process or receiver is not clearly defined due to key contacts changing roles or not having contact with the system's users. And in general, the transfer of knowledge seems to be a key aspect to success, as the long-term viability of the design automation system is dependent on technical knowledge at the receiver side. So with all the 4 papers summarized, it's time for my conclusions, answering my research questions and pointing out some avenues for future work. So research question 1 is, what is the state of the art of optimization-based configurators? And this question has been answered through a literature study carried out as a part of paper 3 and the kappa. And paper 4 also contributes to this question through the multiple case study. So the existing literature indicates that there is large potential in optimization-based configuration for engineer-to-order sales processes, but that it is not fully captured. And some authors point to the challenge of maintainability and flexibility as mostly open issues. And I would claim that clear guidelines and reusable primitives for implementation are missing. So to do something about that, research question 2 starts at finding a path forward. And the question is, which functionalities are needed within optimization-based configurators? And throughout the 2 main case studies laid out in paper 1 to 3, implicit and explicit needs have been captured. And some important examples include enabling configurator users to assess the impact of uncertain and limiting factors, as well as enabling the user to adapt the optimization problem depending on the stage in the configuration process. The development of optimization-based configurators can be aided by providing enhanced support for integrating models, reusing model formulations, and managing data in the pre and post processing of optimization formulations and the resulting datasets. And to be able to handle common issues of design automation system development, there are mapped a high level of maintainability is required. So finally, research question 3 is, how should an optimization-based configuration system be designed and implemented? And papers 1 to 3 document prescriptive studies conducted for different test cases and providing reusable implementation details. And throughout these case studies, optimization and configuration concepts have been continuously developed and evaluated, resulting in conceptual and technical supports for implementing optimization-based configurators in 2 main ways. So primarily through a framework for the conceptual structuring of the routines to be carried out in automated optimization-based configuration, and secondarily by introducing reusable code primitives for the definition of these routines. And these contributions can aid the development of optimization-based configuration systems by providing an overview of the technical architecture and by supporting the definition and integration of models. And furthermore, the provided reusable tooling can be used to partially mitigate the issue of managing model metadata and data in a structured way. And the proposed methods and tools are verified on the basis of 2 case studies and have been shown to demonstrate a practical utility in industrial product development processes. So the research laid out in my thesis has identified and undertaken some of the key activities needed to effectively and efficiently configure complex engineered products through the application of optimization-based configuration. So what benefits can a successful implementation provide then? Well, a structured approach to the optimization-based configuration process that supports automated design exploration in early product development, leading to a clear view of the solution space and what compromises it entails, yielding an accelerated quotation process for complex products, ultimately leading to reduced risk and resource waste in ETO businesses. And to reach this potential to its fullest, some work remain. State-of-the-art MDO techniques can be integrated and extended to support a higher degree of automation when it comes to defining the multidisciplinary optimization problems used. And this could further rationalize the time-consuming activity of integrated models, enabling configuration engineers to focus on model improvement and maintenance, and thus long-term viability of optimization-based configurators. Integration of state-of-the-art concepts such as knowledge objects and high-level CAD templates could aid in the rapid development and integration of flexible geometry and physics models. And the contributions should be applied to other cases to assess and develop their generality. The computational performance can and should be enhanced further to facilitate even faster processes. And finally, the possible implications on business models should be mapped. So can optimization-based configuration make a product as easily configured as the kitchen? And what does that imply for business? So I hope that by applying and developing my findings further, the utility of optimization-based configuration can be captured and enhanced, ultimately leaving product quotes from having the same faith as that one. Thank you.